Amir. Yeah. Hello, everybody. This is Amir from the University of Edinburgh, and I'm going to talk about structured tensor algebra for efficient discrete probabilistic inference. So perhaps I should skip the first two slides. It's on the motivation for probabilistic programming languages, and we are all motivated enough. And perhaps you know that there are two kinds of distributions that we can deal with, continuous and discrete. And today I'm going to just focus on discrete distributions, where there has been an amazing work that appeared, I think 3 years ago now, or 4 years ago, DICE, which actually had amazing results for the scalability of inference for discrete distributions. However, looking at the results for discrete Bayesian networks, we see that, okay, in comparison with state-of-the-art probabilistic languages, it's doing a good job, but if you compare it with specialized tools for inference over Bayesian networks, it's not usually doing a good job whenever we have large Bayesian networks. And the main insight, according to my interpretation for DICE, is that basically somehow you have a logical expression, logical kind of representation for the discrete distributions through binary decision diagrams, or BDDs. And the question, the first part of the question that I'm going to answer today is that there has been massive progress on tensor processing frameworks these years for deep learning applications like PyTorch, NumPy, TensorFlow, and so on and so forth. So can we use these tensor libraries to scale the inference over discrete distributions even better? So in other words, I'm interested in kind of, rather than the logical representation, have the tensor representation for discrete distributions. And this question, we kind of answered it before. It's actually part of our base tensor framework that appeared in the Compiler Construction Conference, where we are taking the DICE program, we are translating it into a functional probabilistic programming language, which we call it base tensor. And then we convert the inference problem over these programs into basically the variable elimination algorithm over the tensor representation of it. And basically, this is a tensor, nothing but a tensor contraction. And then in the tensor frameworks, they have hand-tuned implementations for such computations. And here you can see that, there were quite a lot of transformations involved in order to achieve that. And the result was that, okay, for these Bayesian networks, now we could actually scale it better than what the DICE is doing. And basically, it's going to be very competitive to the specialized tools out there. But now I'm going to introduce two additional challenges. So what if we have arithmetic operations over discrete distributions? So the DICE folks have kind of answered that. They had an amazing paper last year where they were also scaling the integer arithmetic in discrete probabilistic programs. And the other challenge is that what if we have discrete distributions, but those distributions have sparsity inside them? So let me tell you in very high level what we can do in order to translate the arithmetic operations over discrete distributions into tensor algebra. So we basically take the following expression. This is a probabilistic program expression. And we translate it into a tensor algebra expression. So this is known as tensor contraction or Einstein summation. So the trouble in terms of A and B, so they are actually a vector that you can think of like, okay, we have a discrete distribution, so we have actually vectors from the values and the associated probabilities. What is this term M that is appearing here? So this is basically an order 3 tensor, which is basically specifies that it's going to be 0 almost everywhere, except for the places where I plus j equals k, it's going to be 1. So the issue is that this tensor is very, very sparse. And if you use these tensor processing frameworks, they're going to do a horrible job in evaluating such an expression. So basically, if we precisely look into the structure of tensors, so usually in the deep learning applications, you deal with tensors of the left kind, which mostly the elements are non-zero. But in practice, in many applications, we can have sparse tensors, which actually most of the elements are zero, and only some elements are non-zero. And even we can have nicer structure for this sparsity. So for example, look at this diagonal matrix. It's not only the case that only a subset of the elements are non-zero, but actually we know exactly what is the shape of the non-zero elements. So here you can see a bunch of tensor algebra frameworks. On the left side, we have actually the dense processing tensor frameworks, which basically TensorFlow, NumPy, PyTorch are of that kind, and the BLAST routines also are of that kind. However, on the right-hand side, we have this sparsity, which is kind of unstructured. So we know that many of the elements are non-zero, but it's actually scattered through all the places. And here we have somewhere in the middle, we have basically symbolic structure, or structured sparsity. And here I'm mentioning some notable work. The tensor algebra compiler done by MIT folks has basically focused more on the dynamic sparsity side. And actually, we have also some work on the same type of sparsity, but also we had some recent work on this structured sparsity. And here I'm going to briefly mention to you what I mean by that. So look at this diagonal matrix. So we can specify the unique set of the elements, or the non-zero elements, basically, as a tensor algebra expression. So we have tensor algebra, however, we have extended it with some sort of logical expressions here. And this is not the only type of structure that we can capture. Look at this symmetric matrix. So the symmetric matrix also, if we precisely look into it, we basically only need to preserve half of this matrix, okay? Only the upper triangular, for example. And then we can specify the unique set of elements and also the redundant elements, how to reconstruct the rest of the matrix by using the unique elements. And the intermediate representation that we define for this kind of structure is basically very expressive. Look at this gigantic matrix. So with the colors, the unique colors basically are redundant elements. So basically on the right-hand side, you can find a mask of the elements that are, we only need to just preserve them. And the rest of the elements are going to be redundant. So we can basically represent both of these types of structures. So here is the architecture of the compiler for structured tensor algebra. So we give as input the tensor algebra and the input structure. And then we have an intermediate representation that can express both of them. So we can propagate the structure across different tensor algebra operations. We can optimize it, and then we can do efficient low-level code generation. And here I'm giving just one example. So here is one tensor algebra expression, and this is the way that we express its unique set of elements. And basically, we can generate this tight, nice loop for that. So here, the first part of the loop is, actually the loop bounds is specified by the unique set of elements, and the actual computation is derived based on the tensor algebra expression. So to summarize, I presented to you the base tensor, and I have shown you how we can use tensor algebra for efficient inference, but then I introduced two challenges. What can we do whenever we have sparsity in the distributions? So we can use basically sparse tensor algebra, and what can we do for distribution arithmetic over discrete distributions? So then we can use structured tensor algebra. Thank you so much.